All right, welcome to reinforced concrete design. Yeah, we are going to figure out how to design some reinforced concrete members, such as steel, or not steel, such as a beam or column, is most of what we're going to focus on. In this first lecture, it's just more of an introduction to concrete as a material and how it's used in structures, as well as the reinforcing bars. We're not talking about specifically just concrete. It's reinforced concrete, which means there is steel reinforcement in it. So let's work out a little bit of vocabulary here. Often people like to, you hear words and you don't know what the words are from or what they mean, so it's nice to, let's see if that'll make that go away. So let's see, we got here, right, that's a column. Hopefully everybody can figure out a column. Columns are vertical. Here's another column right here. Let's see. This is this whole section right here, the horizontal floor, right? That's the slab. And these little guys are the joists. Joists are smaller. If that might be in steel construction, it might be like kind of a truss looking thing. In concrete, it might be poured monolithically or at the same time. Running the joists run between beams. There's a beam right there. This one right here, this is stairs. I hope you have heard that word before. Stairs and a landing at the bottom of the stairs. Here's another column. Up down here supporting everything, that is a spread footing. Spread footings can be square or rectangular, but they just support one column, maybe two, but then you'll have like a footing that like a wall footing over here. Strip footing, that was the word I was trying to think of. Spread footings usually only support about one column. Let's see what else. Oh, since this you can kind of, hopefully you can see over here on the left, this is the ground line, right? So that means that this is a basement, that bottom level. So this is a foundation wall. Foundation wall. I'm just going to write FDN because that's foundation. You know, it's holding back the soil. Here's what we got. This is the slab on the grade. It's where the slab is fully supported by soil beneath it. Like my house is a slab on grade. I don't have a crawl space beneath it. I don't have a basement. The slab is poured directly on the ground. Right, oh yeah, here's another beam over here. And then this little part right here above the door, a lintel, right? That's holding that opening. You'll have door lintels, window lintels, supporting the wall above the opening. Out here, that's also a beam, but this is called a spandrel beam because it's on the edge. And that'll come into play in senior design. We're going to design spandrel beams and interior beams and girders. Yeah. So, of course, we'll design them with steel, but the nomenclature is still the same. Let's see. It's pretty much all over on that side. Wall, footing, spread footing, yep. Here we have another, right, we have some interior columns. And you can see the columns at the top and bottom have certain things like this is a pedestal, right? At the bottom of the column there. Let's see what else. Some more spread footings down here at the bottom. Another foundation wall, retaining wall. Holding back that soil so that you can have a basement. I guess this is a one-story building, so let's say that this is the roof up top. And here at the bottom we have exterior columns. Right, makes sense, interior versus exterior. And a column bracket up at the top. Those are just, drop panels, that's what those are. These square things right here, drop panels. Those are all like the drop panels and the pedestals at the bottom. Help spread out the load a little bit more so you don't have like such a concentrated force from the column into the floor slab or roof slab. Oh, and this roof, right, that's a flat plate. A flat plate roof. And another slab on grade. These are interior columns. Right? So just getting an idea of the words that we're trying to say here. If you hear these words and you don't know what they are, you can also Google them or ask. And then I'll Google them. So those are all types of things that can be poured and made out of concrete. I guess what you don't notice here, I guess they're possible, but are a lot of braces. Concrete would mostly have a shear wall as its lateral resisting system than braced frames. That would be steel. So let's talk about our objectives for our design. Right? When we're asked to design something, either out of concrete, steel, masonry, or even something not structurally related. We have to keep a couple things in mind. One, appropriateness. Is what we're choosing the right material? Is it going to do what we want it to do? Right, talking about, will it fit? Concrete often takes up a lot more space than steel. But maybe you're in a land where concrete's easier to get than steel. So, will the design we choose fulfill the intended use of the facility? Is it aesthetically pleasing? The architect might have some ideas about that. Yeah. Right? The people who are actually paying to build the building might not want a giant concrete block. Maybe they want something else. So what can we change with what we have available? Two, we'll talk about economy, right? Bottom line is what we're choosing within the budget. Maybe you have a concrete plant down the road, but the nearest steel manufacturer is like 1,000 miles away. So while you might want to use steel, concrete would be a lot cheaper. Maybe labor, you have a lot of people who know how to build with concrete, but not steel, something like that. Is it structurally adequate? That's where we come in, really, at this level. Does it have enough strength? Will it work? So serviceability. That's where we're starting. The project managers, the people that get paid more money, are probably making the bigger decisions about the design as a whole. Although we, as designers and with more and more experience, can answer those questions. As a little first year engineer, what you're going to do is say, use this size instead of this size or something like that. And is there any maintenance involved? Because what if you build something and it needs a lot of work? Maybe it was cheaper to build, but now you got to put more money and time into fixing it. A lot of the failures of steel concrete, in terms of maintenance, is water getting in. There's cracking, water gets in, starts to corrode. The reinforcing steel, concrete might pop off. You got what's called spalling. Do you have to do anything to maintain it? So those are the questions you ask when you're designing your structure. So the limit states for concrete. Now this is overall limit states categories, not specific, not right? In tension for steel, we had rupture and yielding. Those are both under the umbrella of strength, right? Is what you're designing strong enough to hold your the loads? So that's looking at equilibrium, instability. Instability comes into play, if you remember, in steel, right? Buckling. Or any type of buckling, compression causing buckling. Fatigue, if something has a lot of vibrations, cycles of motion, will it eventually cause a loss of strength? Failure, meaning you put too much weight on it and it can't hold it, so it breaks. Let's see, progressive collapse. There's no redundancy in the system. If there's no redundancy, then if one beam breaks, the entire building goes down. You want to have some type of safety factor redundancy in there. I believe redundancy was an issue with the I-35W bridge in Minneapolis, but there was no redundancy. Similarly, I think the Mothman Bridge in West Virginia, yeah, those are failures that might be interesting to look at. No redundancy. And then plastic hinges. Which cause an instability. If you stress a beam too much, you're going to cause a stress concentration and a hinge where you thought you didn't have a hinge before. We had strength, we had serviceability. Serviceability, we're talking about not that it'll fall down, but that the building works in the way you intend it to. One of the big, these are limit states where we're talking about something that will disrupt the functional use of the structure. Like it might not fall down, but the structure won't be able to be used as you intended it. Examples are like excessive deformation, excessive cracking, especially in concrete. That cracking might lead to leaks, corrosion of the reinforcement, and deterioration of the concrete. Undesirable vibration. Maybe you want vibrations, maybe you don't. That is I'll put a link on Blackboard, but I believe the other day in senior design we referenced Galloping Gertie, the Tacoma Narrows Bridge, I'll put a link in it because if you graduate with a civil engineering degree having not watched that video, I think we should revoke your degree. Right. That was an extreme example of undesirable vibration. Right. It gets, it hits reverberation. Finally, we have some special limit states. These are abnormal conditions that might not be applicable, such as earthquakes, explosions, fire, vehicular collision, something that is not likely to happen unless you know, if you live in San Francisco, you might have to design for an earthquake. We don't normally design unless, I mean, depending on the use of the building, this is where, you know, ASCE 7 comes in, and if it would result in a lot of loss of life, or if it's a building that's really important, like a hospital, we might want to design for some of these extreme conditions. But many buildings, you know, like a random office building, is probably not going to be designed for an explosion, unfortunately, in this day and age. But yeah, so strength and serviceability, and then special stuff. Strength and serviceability is generally what we focus on, especially at the introductory design level. Hopefully you guys remember this design approach. It's called, does anyone remember? LRFD. Load and resistance factor design. Where we have our phi factors and our factored loads, right? Our RU is our factored loads. That's where we take all of our loads and put them into load combinations and factor them to find our controlling factored load requirement, controlling combination. Right, this is how much we need. This is how much we have. Hopefully how much we have is more than how much we need. We need to be able to hold a certain amount of load. We have a certain amount of ability to do that. So we have on the left side is our factored loads. That's what we need. On the right side, we have our design strength, our phi RN. And RN is just a placeholder for a different type of strength, right? Like a MN for like a moment flexural capacity, PN for an axial capacity. So that's our design strength. RN is our nominal strength. And we decrease it by our phi factor, which is usually less than or equal to 1. So we need a certain amount, we have a certain amount, what we have better be more than how much we need. So these are the load combinations. Oh, I should flip the page. These are the load combinations. Hopefully you've been familiar with this from steel and from structural analysis. It's table 5.3.1, which if you are in your ACI code, ACI 318, '19 is on page 62. Might be a good place to put a tab. And just as a refresher, we'll write down what these are. Right, D is our dead load. That's everything that's permanent, such as the weight of your building itself. So once you design a building, you have to calculate how much it weighs and include that in your model, in your analysis, to determine your factored loads. L is your live load. That's anything that moves, whether or not it's alive. So that would be people, but it could also be furniture, temporary walls, right? Like your little cubicle walls, those can move, even though they won't be moving. Your desks are probably not moving too much, but yeah, that's your live load. Let's see what else. Your roof live load. That might be like construction or workers on the roof. It's not snow or anything because that's a different one. All right. S is our snow load. R is rain. W is our wind load. All right, that's gusts of wind. Not tornadoes, but hurricanes or any type of wind, right? Since tornadoes are very hard to predict, earthquakes are a little bit more, not earthquakes, hurricanes are a little bit larger. They tend to happen more regularly. And E is our earthquake or our seismic load. So what's interesting, if you look at this table, right, that first combination is focusing solely on dead load, obviously. The second one is incorporating our live load. The third one, that's probably something that you're going to use to design your roof, because the controlling thing in there is a roof load, a snow load, or a rain load, which are all only things that happen on a roof. If it's snowing inside your building, then you got some other problems. And then you see we have our wind and earthquake. You can see in these two down here, we're reducing our dead load, so that's like our uplift cases. Either the wind is forcing something up, or like the diaphragm, floor diaphragms or the roof diaphragms or an earthquake is causing upward motion on maybe one side of the building. Our strength reduction factors are in chapter 21, table 21.2.1. Again, another good place for a tab. It's a whole chapter on strength reduction factors. Starts on page 391. We are mostly going to be utilizing this first one because this is what we use for moment, flexure, whatever you want to call it, beams, axial force, so columns with our compression. You're not likely to use concrete for tension. I wouldn't recommend it. It's not very good. But it could be, right? It could be subjected to tension or compression, like in an earthquake or something. But I wouldn't use reinforced concrete as your tension brace. It's moment, axial, moment plus axial. And you can see right here it varies, and we're going to have to figure out how to calculate that. It's going to vary. It's going to depend on if your section is tension controlled or compression controlled. And there's a way to figure that out, right? It says, look at 21.2.2, and we're going to get into that, so don't worry, you don't have to do it now. But those are the ones we're going to focus on, and then shear as well. The rest start to get into the next concrete design course. So moment, axial, and shear are what we're going to talk about. And a lot of it is going to be moment. So yeah, that's your fee factors. Yeah. Let's see. Let's talk about dimensions. When we were previously designing for steel, the steel manufacturers all say, here are the sizes available, and you don't get any say in anything. When we're talking about concrete, you as the designer get to say how big something is. With that in mind, you do have to follow a few rules of thumb. We're going to keep our cross-section dimensions that's like our width, depth, height, whatever you want to call it, in whole inches. You're not going to have a beam that's 13.5 inches wide. We're going to have slabs, right? Our floors and our roofs. The thickness of them is in 1/2 inch increments. And the length of the reinforcing steel, so we're going to put these long bars in our concrete, right? Let's draw a little cross section, right? Here's a little cross section, and those are our little reinforcing bars. And then if you look at it along the length, you have these reinforcing bars. This is an elevation, but right, reinforcing bars. The length of them in 2-inch increments. So here is a stress strain curve of concrete, or normal weight concrete, right? Over here is the tension side. Tension. And then this is the compression. Oh, there's the. So pretty easy to see. You wouldn't really want to design too much. You wouldn't want to rely on your concrete by itself for any tensile strength. Concrete is typically used when it's in compression. We have a bit of a normal stress strain curve, or what's that called? Elastic. Elastic stress strain, and the you get an elastic modulus, then it begins to yield, and eventually you reach a peak compressive stress. This is called F prime C. This is a symbol that you will be using for the entire semester. F prime C is your peak compressive stress of your concrete, and it ranges from about 2,500 psi to 5,000 psi. You can make stronger, you can probably make weaker. But when we're using our design values, we typically estimate 4,000 psi is usually, it's often a number used. So F prime C is your peak compressive stress. Your maximum tensile stress down here is about 300 to 700 psi. Right. So we're talking about an order of magnitude between their tensile strength and compressive strength. to estimate the elastic modulus of concrete EC, we go to, there's an equation, ACI 19.2.2.16. Or 0.1 B, oh not 16 B. ACI 318.19, page 356, 19.2.2.1 B. It's a B, not a 6. You can calculate the modulus of concrete as EC equals 57,000 square root F prime C. Now here's another little thing that you're going to have to keep in mind in concrete. It's a square root. This value right here needs to be in PSI, and the result will be in PSI. So don't put 4 KSI, put 4,000 PSI. This is very, very important to remember. PSI under the square root every time. Always PSI. Okay? And it'll come out PSI. These are empirical formulas that have been done by researchers, and they are unit dependent. Circle this, put like giant sparkly things, okay? Under the square root is always PSI, and it comes out PSI. That's not how real math works. That's how ACI empirical math works. And this is for normal weight concrete. B is normal weight concrete, which has a weight of about 150 pounds per cubic foot. There's lightweight concrete and there's normal weight concrete. Actually, it might be 145 PSF and then 150 if you include the reinforcement. Still. Anyway. I don't know. Okay, so that is the stress-strain relationship of concrete. How do we determine our material properties? We make cylinders of our concrete and apply a compressive load. Our cylinder has a certain diameter. I think it's usually about 4 inches. Or 6 inches. That's right, 6 inches. I have it actually written down. Right? we do 6-inch diameter by 12-inch height cylinders. We cure them for 28 days, meaning put them in a controlled environment, a controlled temperature, controlled humidity. If you're doing this out in the field, you might also keep a couple cylinders in the field conditions. So you have your lab controlled ones and then your field ones. Cure them for 28 days. And then we break them with our compression test. Right? Stress, force over area. And we get our load at failure. And that gives us our F prime C. Usually take the average of at least 2 cylinders. So you mix up your concrete, you make a couple cylinders, you put them, you let them cure, get stronger. It'll usually set in about a day, right? It'll be hard, but it's not fully cured for 28 days. You might also do a break at like 7 days, but it'll get stronger from over the time. Again, I think it gets most of the strength in 7 days, but it'll get stronger over 28. Another test is the tensile test. This is the modulus of rupture test, a 3-point bending specimen. I don't know if you guys talked about any of this in your materials classes. Hopefully you did. But just in case you didn't, right? This is our 3-point bending. If you apply, you have a support, 2 supports, and you apply a force, you're gonna have positive bending, causing tension right down here at the bottom, and fracture. You get to calculate the modulus of rupture, which is the force at which that fracture begins to occur. Might also do the split cylinder test. That's the one on the right. Where you're supported along the length and you apply a load on the top. And it causes, if you look at the cross section, right, you have your load, your other load. The flow of the forces is like that. And if you right, the resultants look like that. So you have compression acting vertically, but tension acting horizontally. Right, this is the tension. It's going to cause a crack through the center. And you get to calculate the modulus of rupture from that too. So that's 2 ways of determining the tensile properties of steel, of concrete. Usually these cylinders are what you're going to look at a lot. So along with changes in strength, a lot with time. You have volume changes. You have shrinkage, which is a decrease in your volume during hardening and drying. Right? The cement reacts with the water and creates the glue to hold the aggregate and the fines all together, which is what concrete is made out of. As there might be excessive water, so it might dry and evaporate and get smaller overall. So with time, there's some shrinkage strain. You have a lot at the beginning, and then it evens out over time. Right, it'll start to get drier and drier, so there's less shrinkage. Creep is when it slowly. Creep is due to loading, right? Slow strains over time due to sustained loads. So if we look at our time and our creep strain, you have your building, you don't have any loads, everything's fine. You apply a load, bam, you immediately have deflection. Right, this is when we apply our load. You have immediate deflection. And then over time, you get a little bit more deflection. You can break this down into your elastic strain, initial, right? You apply a load and bam, there's an initial deflection. And then your creep strain, which happens over time. Yes, this is not creep strain, this is overall strain. Then let's say we remove our load. We're going along, we remove our load. We recover that elastic strain. And slowly, we might also recover some of that creep strain, but maybe not all of it. This is our elastic recovery. And then our creep recovery. And there's probably some permanent or plastic deformation. And this is when we remove our load. So 2 different types of time-dependent volume changes. One, due to the material itself shrinking, so that's material dependent. And then creep, that's load dependent. And I guess based on the material, but not the material by itself. Right, you apply a load, immediately it deforms, and then over time it deforms a little bit more. You remove the load, you immediately recover some of that, your elastic recovery. You might recover a little bit more over time, but there might be some permanent deformation. Whereas the shrinkage is there forever. Finally, we have our reinforcement, right? This is reinforced concrete, not just plain concrete. So we have our bars, our steel bars. There are some of these on campus in 233, but they often have this little spiral pattern on them. This H is the letter or the symbol of who produced it. Who made this bar? Then we have our bar size. This is a number 11. This is the type of steel that was used to make the bar. The material and all that. And then this is the grade or the yield strength. For example, this is a number 11 bar with a yield strength of 60 KSI. Other values are 40 KSI and 75. The numbers that we will be using are the grade, the FY, and the bar size. We don't, at the moment, don't care where it was made or what it was made out of. We just care about how big it is and what its yield strength is, because how big it is tells us its diameter and its cross-sectional area, which we can use to calculate the strength, right? Yield strength times area will give us a force. So the number and the grade or the yield strength. Finally, this is a big tab. You are going to want to have this tab, okay? In ACI 318, Appendix B, we have our reinforcing sizes. It is on page 581. These are the sizes that you will be using. It goes from 3 to 18. You see it doesn't have every number. 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, and 18. The nominal diameter up to a number 8 the nominal diameter is the bar size divided by 8 in inches. So a number 3, for example, the diameter is 3/8 of an inch, right? 0.375, 3 divided by 8. A number 4 is 4 divided by 8, so it's 1/2 of an inch. So a number 8 divided by 8 is 1 inch, right? 1 inch, 1/2 an inch, 3/8 of an inch. Beyond that, it's almost but it's not quite exactly. When you are calculating when you are using the areas to calculate forces in the reinforcement, do not do pi d squared over 4 using these diameters. Don't do that. The area of the bars is not equal to pi d squared over 4. You would think it would be, but it's not. Right, do not do that. Use these values. You might start to memorize some of them, like a number 8 is 0.79 inches squared. This is the area of the bars of the steel. Number 8 is 0.79. What's really convenient is number 8 is 0.79. That's one that you might end up using a lot. And a number 9 is 1 square inch. And number 10, you see the diameter is 1.27 and the area is 1.27. This is a tab that you will use all the time unless you have this memorized. It is often a table that is up on the walls of a structural engineer who designs concrete, for a quick reference. So that is our reinforcement. So that is the introduction to the materials and the design philosophies that are used in reinforced concrete design. After this, we will start into flexure. Flexure will be at least half the class because it's a lot of information that's applicable to the rest of the design. So with that, I will let you guys go.